In the previous video, we had discussed about dispersion or London forces. In this video, we are going to be talking about dipole-dipole forces. So dipole-dipole forces, as the name suggests, we obviously know it involves a dipole moment. So these forces are exhibited by compounds or rather molecules which have a dipole moment. And the examples include water. Oh, I am so sorry. Oxygen is in the center, not the hydrogen. Hydrogen can't even form two normal bonds. Anyways, so oxygen, hydrogen, and hydrogen. So basically, oxygen is more electronegative than hydrogen. So what happens is the dipole moment is towards the oxygen atom. Right, so this means that water on the whole has a dipole moment, and the forces that is shown by these molecules is called as dipole-dipole forces. Excuse me. Now we're taking the example of HCl, okay, hydrochloric acid or hydrogen chloride if it's a gas. So in this molecule, we obviously know that chlorine is more electronegative than hydrogen. So what happens is chlorine will have a partial negative charge, which is denoted as a delta minus sign, whereas a hydrogen atom has a partial positive charge. And this diagram basically represents the presence of a partial negative as well as a partial positive charge. So now, when two molecules of HCl come close together, they will orient themselves in such a way that the partial negative charge of the chlorine and the partial positive charge of the hydrogen are close together. And this leads to the formation of the dipole-dipole force. So this is the dipole-dipole interaction between two HCl molecules. Now this is mainly due to the presence of the interaction between oppositely partially partial charged parts of the molecule. Now, one important thing we need to remember is that the partial charges are obviously going to be lesser than that of the electronic charges. So, electronic charge is 1.6 into 10 to the power minus 19 coulombs, and partial charge will always be less than that value. So, because of that, these forces are stronger than the London forces or the dispersion forces. As you remember, we talked about instantaneous dipole and induced dipole. So these forces are stronger than that one, but they are weaker than the ion-ion interactions. So when two ions come close together, they lead to the formation of an ionic bond. So these forces, dipole-dipole forces, are weaker than the ion-ion interactions. Also, one very important thing is that the attraction obviously will decrease with increase in the distance. So obviously, if these HCl molecules, assuming this is where they are present. So if I had a HCl molecule here and another here, then obviously the extent or the amount of attraction between these two molecules would be lesser. So the forces decrease with increase in distance. Also, the interaction, so this particular type of force was studied by Keeson in 1912, and he called it orientation effect. Now, according to this, the interaction energy is inversely proportional to the distance. So in the previous one as well, we learned that the interaction energy for the dispersion or London force was inversely proportional to to r to the power 6, right? So similarly here, the interaction energy between a stationary polar molecule, so if it is in the solid state, the interaction energy is going to be inversely proportional to r to the power 3. Okay, this is in solid because the polar molecules are stationary. Stationary, yeah. ERY means it's the shop, ARY is the... Okay, anyways. Whereas if these molecules are rotating, then the interaction energy becomes inversely proportional to 1 by r to the power 6. This is for the rotating polar molecules. So the polar molecules, not only do they possess the dipole interactions, but they also possess the London forces. So they don't just interact with the dipole forces, but they also have some amount of dispersion or London forces. Okay, so dipole forces, they are shown by molecules which are polar in nature. The previous one was shown by non-polar molecules. These are shown by polar molecules. So here we have HCl. H is less electronegative than chlorine. So obviously chlorine gets a partial negative charge, whereas hydrogen gets a partial positive charge. So the partial negative charge on the chlorine atom will be less than the electronic charge, right? So here you have two molecules of HCl. Here, so these two molecules interact by the dipole-dipole interactions. So the chlorine, which is partially negative, will interact with the partial positive of the hydrogen. These forces are stronger than the London or dispersion forces, but they are weaker than ionic forces. The reason for it being that weak is because it only involves a partial charge. See, ion-ion interactions involve a complete, like you don't put a delta sign in, when you write Na plus and Cl minus, we don't put a partial positive and a partial negative charge on these two atoms. They have a positive and a negative charge. So because of that, dipole-dipole forces are actually weaker than the ionic forces, but they're stronger than the London forces. But one thing is similar between the two of them is that the distance. If the distance between the two molecules increases, then obviously the strength of the dipole-dipole interaction will decrease. Now the interaction energy of when the polar molecule is stationary is inversely proportional to r to the power 3, where r is the distance between the two molecules, whereas if it is the rotating polar molecule, then it is inversely proportional to r to the power 6. It was first studied and given by Keeson in the year 1912, and he called these orientation forces. In the next video, we will be discussing about dipole and induced dipole forces. One thing I suggest, if you find these topics difficult, go back to the introductory topic about the intermolecular forces, where I've discussed about the basic differences between polar and non-polar, what is a dipole, and maybe that will help you understand it. So do check out the next video on dipole and induced dipole forces.